Our next speaker is Dr. Laura Henderson. She's going to talk about entangling 3 detectors in a black hole spacetime. Laura, whenever you want, the floor is yours.
Great. Well, thank you for the organizers for doing this in, I think, record time. So it's good. It's nice to have another one of these conferences. So just a sort of brief warning with this talk. There's a lot I wanted to put into this. My first draft was 40 minutes long. My second draft was 20 minutes long. Hopefully this third draft will fit well into the 12 minutes. So I'm going to have to skim over some things and probably oversimplify a few things, but hopefully I can clarify those in the chat later. So my talk is entangling 3 detectors in a black hole space-time. So why do we care about detectors? The idea is to probe quantum fields on curved spacetimes, and quantum fields on curved spacetimes are nice because they're treating the quantum field and gravitational effects, both with physical significance, and may provide clues on what we can expect from a true theory of quantum gravity, whatever that may be. And as I said, detector models, they provide an operational approach to probe some properties of fields such as temperature, entanglement structure. And they do that by locally sampling the fields. And one thing that, as Rob mentioned, they can do is they can extract, a pair of detectors can extract field entanglement. And that was shown all the way back in 1991. And there's been many, many, many papers since then investigating the entanglement harvesting by a pair of these localized UDW 2-level particle detectors, UDW detectors. And sort of one result that is that led to this talk is the fact that a pair of detectors cannot become entangled through any kind of interaction with the field if they're too close to a black hole horizon. And that region is known as the entanglement shadow. And we can also harvest multipartite entanglement or n-partite entanglement. It's been shown in 2005 by Simon Resnick that you can swap n-partite entanglement to n-detectors, and that can be distilled to a W state. But not a lot of people have looked into that. One of the first papers was by Lorak and collaborators, where they used Gaussian quantum mechanics to extract genuine tripartite entanglement from a vacuum of a periodic cavity. And then sort of some more recent work was done this year that showed that 3 UDW detectors can harvest genuine tripartite entanglement in flat space from the flat space vacuum, both with instantaneous, so delta switching, and Gaussian switching. So they couple to the field in a Gaussian switch. And sort of one theme of all of these tripartite entanglement papers is that it's much easier to harvest tripartite entanglement than bipartite entanglement. So we know, one, that a pair of static detectors can't become entangled, or they can't harvest entangled if they're too close to a black hole horizon. But 2, it's much easier to harvest tripartite entanglement than bipartite entanglement. So that's going to lead the question that I'm hoping to answer is what happens to the entanglement shadow when tripartite entanglement is considered? Is there one? And if so, where is it? So just to briefly talk about what the entanglement harvesting protocol is, just in words, you have at least 2 uncorrelated UDW detectors, and then you allow them to locally interact with a free quantum field, usually the massless scalar field in a quantum state, at some place for some time. And after the interaction, the detectors may become entangled, and that's true even if they're space-like separated for the entire interaction. The entanglement was swapped from the field to the detectors. So to make the interaction a bit more precise, here's the interaction Hamiltonian, where you've got your coupling strength is small and the switching function. And for this case, so we're going to take the switching function and the energy gap, so the difference between the ground and excited state, to be defined in the detectors frame. So you can imagine you've got a box of these detectors that you're putting in curved space-time, but the energy gap is set. And it's interacting locally at this position XD. And sort of the last piece of this puzzle is how are we going to quantify this tripartite entanglement? And this is where I'm going to probably be a bit vague and possibly oversimplify some things, but for the purpose of this quick talk, we're going to use the pi-tangle to provide our measure of tripartite entanglement. So that's the average of sort of pi A, pi B, pi C, where, for example, pi A is what we've been calling the tripartite negativity of A with BC, the BC subsystem, minus the negativity of A with B and A with C. Similarly for pi B and pi C. So we can interpret these quantities loosely by saying that if you have tripartite entanglement, that means that A is more entangled with the BC subsystem than with A with B and B with C alone. So that basically that this tripartite entanglement can't be explained by the bipartite entanglement, the 2A entanglement. And just a quick note on these negativities. So as I said, A with B is the negativity between A and B, so that's 2 qubits. And A, BC, that's the negativity, I'll be calling the tripartite negativity of A with the BC subsystem. So in this case, you've got a 2 qubit, you've got negativity between 2 qubits, and that's an entanglement monotone. But in this case, you've got a qubit and a pair of qubits. So all you can say in this case is if this is greater than 0, you've got the PP partial positive transpose criterion for those who care. For those who are familiar with this, but what you need to know is if this is positive, then you know that A is entangled with BC, but the converse isn't always true. You can have A entangled with BC and still have this negativity B0. So the pi tangle is going to put a lower bound on the tripartite negativity in the system. Because we're working with a mixed state, the pi tangle can become negative. That's not the case for a pure system, but that is just inevitable for working with a mixed state. So we're also going to be more interested in regions of the parameter space where the pi tangle is positive, because that means we are guaranteed to have tripartite entanglement in the 3 detector system.
4 minutes, Laura.
Thank you. So then just to quickly go through, we've got the BTZ black hole, which is a solution, a 2+1 solution to the Einstein equations. It's got no charge. It has a horizon at LM. It's asymptotically ADS, where this L is the ADS length. And we use it because it makes it very easy to calculate the final state of the 3 detector system. So the first configuration we're going to consider is aligned. So we've got A, B, and C, and they are going to be placed closer and closer to the horizon. They're going to couple to the field through Gaussian switching, and in their reference frames, they're going to have identical identical energy gaps. So what we see, sort of the big result is that on the left, we have the tripartite entanglement. On the right, we have bipartite entanglement between A and B, which are the closest to the horizon. And you can see that the entanglement shadow is much, much smaller in the case of tripartite entanglement than bipartite entanglement. And in fact, for this particular choice of parameters, there may not be an entanglement shadow at all. So just quickly to sort of think of what's happening is when you have this very small entanglement shadow, it looks that tripartite negativities are they die off, they go to 0 much closer to the horizon than the bipartite negativities, and that's giving you the positive pi tangle. And in the case where you don't appear to have a entanglement shadow at all, you actually have the few of the tripartite negativities actually staying positive even as A approaches the horizon. And it's only in the case that when A is at the horizon that it's removed from the system and your negativity of BAC and C with AB is equal to just B with C. And at that point, your pi tangle is 0.
2 minutes, Laura.
Perfect. Sort of the second configuration, one of the reasons that the bipartite entanglement shadow showed up is because there is significant relative redshift between A and B. So we're going to increase the redshift between A and C by keeping it fixed outside and then just moving the 2 detectors closer to the horizon. But that in that case, you still see that there are some cases where you don't have this tripartite entanglement shadow, or it's much smaller than the bipartite entanglement shadow. And this divergence you see here is in the coincidence limit when detector B would be on top of detector C. And then finally, as promised, just quickly, the third configuration we're considering is this equilateral triangle. It's a very symmetric configuration. And what you can see here is there's only very small regions of the parameter space where you have this, where you're guaranteed to have positive pi tangles, so you're guaranteed tripartite entanglement from moderate distances from the horizon, detector distances from the horizon. So this appears to be very sensitive to the black hole mass and the ADS length. And there's a similar sensitivity for energy gap with the detector. So that, again, went through that relatively quickly, but here are the conclusions. And if, again, I'll answer any questions on the Slack channel. So thank you.
Thank you very much, Laura. Thank you.